All right, everybody, we're on notes number 16. And yesterday you were introduced to the word derivative as the word that means finding the slope of the tangent line to the curve at a point. And we learned a method that was something like the limit as x approaches a of f of x minus f of a over x minus a. Well, today we're going to learn a slightly different way to do it with different notation. It's the same general idea, but sometimes one type of notation works better for a problem than the other type, and sometimes it's just a matter of personal preference. So once again, we have some function f of x. We're interested in finding its rate of change at a particular point, and so we might call that point a f of a. So what we need is a second point on the curve, and here's where the notation differs. I'm going to say that the second point is a distance of h from the first point. So right here we have the point a plus h, comma, f of a plus h. And so the secant line between those 2 points, if we find its slope, then we can use that to approximate the slope of the tangent line. But as those 2 points get infinitely close together, then the secant line slope will approach the value of the tangent line slope. So we want h to head towards 0 because we want to make that gap infinitely small. Now, if we're just finding the slope of the secant line to give us the average rate of change, then we don't care about the limit. We just take the difference in the y values, which would be f of a plus h minus f of a over a plus h minus a, so y2 minus y1 over x2 minus x1. Although, look at that denominator. We could cancel the a and the minus a, and it's just h. So I'm going to simplify that. So that is the slope of the secant line, and if we want the slope of the tangent line, then we need to take the limit as h approaches 0. We want those points to get infinitely close together. So here's another definition of derivative. The limit as h goes to 0 of f of a plus h minus f of a over h. That gives you the instantaneous rate of change at the point a f of a. So that's the formula we'll be using today. And as we work through the examples, I'm going to do the same examples that we did yesterday because I want you to see that you get the same answer doing it a different way. And I want you to see the pros and cons of each method. So here's number 1. We're finding the derivative of f of x equals 2x squared at x equals 2. So we're using the limit as h goes to 0 of f of a plus h minus f of a over h. Now a is 2 in this case. So what's f of 2? F of 2 would be 2 times 2 squared, so that's 8. And what's f of a plus h? That's f of 2 plus h. So we need to put 2 plus h in place of x in the function. So that part's a little bit more complicated. So if I write out my limit, I have the limit as h approaches 0 of 2 times 2 plus h quantity squared, that's f of a plus h, minus 8, that's f of a, over h. Okay. So now we simplify the numerator, and we're going to get it to a point where we're going to be able to cancel an h from the top and the bottom. This should look like some of the limits that you've done in the past chapter, where right now if you plug in h equals 0, you get 0 over 0 and it's indeterminate. However, if you simplify and reduce, you'll find you're able to substitute the 0 in there. First of all, we need to FOIL. We need to multiply 2 plus h by 2 plus h. Don't just distribute the squared sign. That's not mathematically equivalent. So when we multiply that out, we're going to end up with 2 times 2 times 2 is 8, plus inside is 2h, outside is 2h. Add those together, you get 4h times 2 is 8h, plus last is h squared times 2 is 2h squared, minus 8 over h. If things go according to plan, you should always have a scenario where you have the constant numbers canceling. We have 8 minus 8. So that leaves us with two terms in our numerator that both are a multiple of h. So we can factor h out of both terms, and that gives us h times the quantity 8 plus 2h over h. Now we can cancel the h from the top and the bottom. What I don't want you to do is go back to the previous step and just cancel everything all at once. Then it's going to look like that, and a person looking at that doesn't really know what happened. So one kind of canceling per step. Okay. So now from here, once I've canceled the h, I can go ahead and substitute the 0 in for h. 8 plus 2 times 0 is just 8. So that tells us the derivative at this point is 8. The slope of the tangent line to the curve at that point is 8. And if you look back at yesterday's notes, that was the answer. Number 2. Here's the function f of x equals x squared minus 4x. We're finding the derivative at x equals 1. So we're going to use the limit as h approaches 0 of f of a plus h minus f of a over h. And in this case, a is 1. So let's find f of 1. 1 squared minus 4 times 1 is negative 3. And let's find f of 1 plus h. So we need to take 1 plus h and square it, and then subtract 4 times 1 plus h. So we're going to FOIL to square this, and we get 1 plus 2h plus h squared, and then we're going to distribute the minus 4, so we get minus 4h. Now typically I'm doing those steps of simplifying within my limit, so I just kind of got carried away there. So we have the limit as h goes to 0 of 1 plus h quantity squared minus 4 times 1 plus h minus negative 3 over h. And then I had already started to simplify that. Remember, always use limit notation until you get to the end where you plug in the number. So that was 1 plus 2h plus h squared minus 4h, and then at the end we have plus 3 over h. Notice your constants. 1 minus 4 plus 3, that adds to 0. So just like we expect, the constants add to 0. I'm going to combine like terms in the numerator. We have 2h, we have minus 4h, so I'm going to combine those. So we have h squared minus 2h on the top and h on the bottom. So now let's factor h out of the numerator. We have the limit as h goes to 0 of h times the quantity h minus 2 over h. And so that we can cancel those h's on the top and the bottom, and now substitute the 0 in, and our answer is negative 2. That's what we got yesterday when we did this problem. Number 3, we have f of x equals 1 over x minus 1. We're finding the derivative at x equals 2. So once again, the limit as h goes to 0. Now I'm purposefully writing this over and over. If you write it over and over, it helps you remember it. And this is something that you want to memorize. Now our a value is 2. So f of a is going to be f of 2. 1 over 2 minus 1 is just 1. And then f of a plus h is f of 2 plus h. So that's 1 over 2 plus h minus 1. So let's set this limit up. By the way, 1 over 2 plus h minus 1, you can combine the 2 and the minus 1, so we just have 1 over 1 plus h. So we have the limit as h goes to 0 of 1 over 1 plus h minus f of 2 is 1 over h. Here's one of those scenarios where we have a fraction with fractions inside, so we're going to multiply the top and the bottom by 1 plus h. Of course, this is after you try direct substitution, and of course direct substitution leads you to 0 over 0, as it tends to do in these problems, so we're looking for a way to simplify. Multiply 1 over 1 plus h by 1 plus h, and all you're left with is 1 minus, multiply 1 by 1 plus h, nothing cancels, put parentheses around it so that you don't forget to distribute the minus, and then just leave the bottom factored. Now let's simplify the top. We have 1 minus h when we distribute that negative sign. And of course 1 minus 1 is 0, so we have the limit as h goes to 0 of the opposite of h over h times 1 plus h. So we can cancel the h's. Just don't forget you have a negative 1 on the top. And now we can substitute the 0 in there. Negative 1 over 1 plus 0 is just negative 1. So that's our answer to that one. And number 4, f of x equals the square root of x. We're finding the derivative at x equals 1. Using the limit as h goes to 0 of f of a plus h minus f of a over h. In this case, a is 1, so f of 1, which will be our f of a, is the square root of 1, and that's 1. And f of a plus h is going to be f of 1 plus h, which is the square root of 1 plus h. Okay, so putting all that into the limit, we have the limit as h goes to 0 of the square root of 1 plus h minus f of 1 is just 1 over h. If you substitute 0 in for h, you get 0 over 0, which is indeterminate, so you have to do something else. And we know the something else that we typically do when we have a radical involved in a difference is we use the conjugate, the square root of 1 plus h plus 1 over itself, special form of 1. So when we multiply the conjugates to get our numerator, we end up with 1 plus h minus 1. And then in the denominator, we're just going to leave it factored. Simplify the numerator, and all you have is h. Reduce the top and the bottom. Don't forget to leave a 1 on the top. And then you're ready to substitute 0 in for h, and we have 1 over the square root of 1 plus 1. That would be 1 over 2. And the answer is 1/2. I think that's the last example. Okay, I do want to point out a couple things. Some books and some mathematicians will use something like this. Instead of using an h, they use delta x. And maybe instead of using an a in the formula, they use an x. So the limit as delta x goes to 0 of x plus delta x minus f of x over h, oops, not over h, over what? Over delta x is the exact same thing. We've traded out h for delta x. Delta means change, and we're talking about a very, very small change in x as the change in x goes to 0. Also, there's nothing special about the letter a in our formula, so I could just as well say the limit as x goes to 0 of f of x plus h minus f of x over h. It's the same formula, and you'll see tomorrow in the lesson that we'll start to generalize, and we'll use that as our general form instead. When we have the a in there, it implies a specific number being plugged in, but when we have x in there, it implies that we're just doing it in general. So we'll leave the rest of that for tomorrow, and here is today's assignment. Thanks, everybody.